Hello guys and welcome back to my YouTube channel. Today we will be discussing a few topics, so let's actually just dive in, alright? First, we will be discussing LLDP, or Link Layer Discovery Protocol. So LLDP allows you to actually share or get information from your neighbor, like directly attached neighbor. It doesn't work with your neighbor's neighbor. Just like in your home, you only know the two houses that are around you. You wouldn't know the second house away from you. You've never probably even seen them bringing their groceries, right? You wouldn't know anything from them or anything like that. It's also vendor neutral, unlike CDP, which is also a neighbor discovery protocol, but that's Cisco proprietary and only works with Cisco devices. While LLDP is vendor neutral, it can work with Juniper, Arista, so on and so forth, right? It operates over Ethernet. LLDP sends and receives packets LLDP DUs over Ethernet frames, ensuring compatibility with most modern networks. It provides visibility into the network topology, helping with troubleshooting, configuration, and inventory management. It is very helpful for troubleshooting because you can see which interfaces directly connect to what devices and if they have an IP address, or just as well as help you actually do the configurations like adding or having them port channel, things like that, right? LLDP is layer 2. It operates at the data link layer and works exclusively on layer 2 of the OSI model. Again, it says direct neighbor connect communication. Only exchange is information between directly connected devices like switches, routers, and endpoints. Not your neighbor's neighbor, just the device that's directly next to you and directly connected. All right, and LLDP packets or LLDP DUs are sent as part of the Ethernet protocol as a unique Ether type 0x88CC for identification. LLDP does not rely on layer 3 protocols like IP for device discovery, ensuring compatibility in any layer 2 network. LLDP use cases. It identifies and documents physical connections between devices, helping visualize the network topology. We've used it many times. If you've seen some of my videos, I've used it many times to actually see the map port channels to see which channel, or not channel, which interface I need to add an IP address to as it connects to a router, things like that, right? Very useful for troubleshooting and configurations. It simplifies diagnosis by showing information about directly connected devices like IDs and system names. See, this is the example. The device ID is the host name of the device that you're actually connecting to. The local interface, it's the interface on the device that you're currently on. So like on switch 1 here, these are the interfaces that it's connecting, or excuse me, the interfaces that it has. Local interface means locally on the device that you're on. Hold time, that's the timer until excuse me, that's the timer. If this timer expires, it will be removed from the LLDP table. The capability, it tells you like what type of device. B's for bridge, or can also be a switch, because they're all this switch right here. Switch 1 is connected to all switches, so switch and bridge interchangeably here. Compatibility. And the port ID is the interface that it connects to on the other device. So on switch 4, let's find switch 4. Where? Here. Switch 4, it connects this device. Switch 1 connects to switch 4 via. Is it really switch 4? Does it have a connection to it? Let's get a better example. Switch 2. Right here, it's local interface. The interface locally on the device that you're connected to is Fast Ethernet 02, and that interface connects to Fast Ethernet 02 on switch 2. So this connection right here. Very, very useful protocol. And then let's go into spanning tree. It's a very, very good protocol right here. So what is spanning tree? So spanning tree is a layer 2 technology that changes the roles of ports as well as devices to discard or logically discard or bring down the interface to prevent redundant paths. And it does this because of broadcast storms. And what broadcast storms are so excuse me. So what broadcast storms are, so since layer 2, its its data doesn't have a TTL or time to live like layer 3 does. Layer 2's traffic, the data link layer, which is where spanning tree operates at, will be pushed around the network indefinitely. So it could continue to be forwarded, regardless of how many times it's done it. It's indefinitely. It does not have a time to live. And that's where spanning tree comes in. It puts certain ports in a blocking state, allowing for that STP traffic, or the BPDUs, the broadcast traffic, to hit that port and then be discarded, preventing loops and broadcast storms, right? And that's amazing about spanning tree. So let's actually get into these slides, right? So spanning tree is a network protocol that prevents loops in Ethernet networks. And then we'll actually show you what a loop is in a bit as well. It ensures that only active paths exist between network devices by blocking redundant paths. It's really good, right? STP dynamically adapts to network topology changes to maintain a loop-free network. It used in layer 2 networks for redundant links are necessary for fault tolerance. Let's scroll down. All right, so this. I just want to show you this, and then we'll go back up to the other slide. So this is a loop, right? A loop is when 3 devices connect to each other and somewhat create like a circle, right? So without spanning tree, let's say this one needs to get to, it receives an unknown unicast frame, which when a switch receives that, it's going to send that out of all its interfaces except the ones that it received it on. So let's say it sends it here, it gets it here, it's going to send it here, this one's going to send it here, and it's going to continue to do that over and over and over. And remember, layer 2 traffic doesn't have a time to live, so it's going to do that indefinitely or infinitely, right? And what spanning tree does, it's, let's say, this interface right here. It's going to get, it's actually, this, and then I'll actually draw on it. So let's say this interface right here, it's in a blocking state. So let's say this one receives the packet again. Unknown unicast frame, it's going to flood it out of all the interface except the ones that it received it on. So it's going to go through here. It's going to flood it here out of this one, and then this one's going to flood it out of this one. But remember, since this is in a blocking state, the packet will just be discarded, right? It will just be dropped. Why? Because STP blocks it to prevent loops. Because if this wasn't blocked, as you can see here, it's going to just continue to flood indefinitely, right? And then let's say that, let me go back. All right, remember, let's say this one was previously blocked, or this one's blocked, and then this one goes down right here. STP will actually be able to dynamically, without human interaction or configuration, be able to adapt to it. So instead of sending traffic this way, it's going to send traffic this way. And this port will become unblocked right here. And then go back to this. This one will actually be blocked because it will dynamically adapt to the changes in the, it will dynamically adapt to the changes in the topology alone, which is pretty cool, right? Similar to how OSPF can change its routing table to find better routes to the same destination, right? So it's going to change it here. This one's going to be blocking, and it will adapt to network changes, right? So if it can't reach this device through how it was previously, through this way, it's going to send traffic this way and still get to that device. All right, so let's get back to here. Oh, as well, I don't know if I said it earlier, but this is a loop, right? When all devices have one connection to each other like this. Okay. I think we'll scroll back down here. So what is spanning tree? Ethernet does not have a built-in loop prevention mechanism leading to broadcast storms. And that's how, what we did earlier, how it gets forwarded out of every interface except the ones that it received it on is going to continue to do that, and that's what causes a broadcast storm, right? Without loop preventions, frame can circulate indefinitely or continuously, infinitely, because there's no stopping mechanism for these broadcast frames since layer 2 doesn't have a time to live, right? It can consume bandwidth as well as probably overload the switch as well. Network redundancy is necessary for high availability, but it introduces loops. STP helps balance redundancy with loop-free network design. Remember how we said earlier that if this one goes down, or excuse me, let me do it again. Whoops. Right, remember how we said earlier this one was blocking? And then if this one goes down, this will no longer be blocked. It will be in a forwarding state. And then this one will be blocked. Right? So it will dynamically adapt to changes in the network, like the interface is going down, new devices being added, things like that, right? Which is amazing. All right, and a broadcast storm. A broadcast storm occurs when excessive broadcast traffic overwhelms the network. Ethernet or layer 2 traffic does not have a time to live mechanism, right? So it's going to be pushed around the network indefinitely. So broadcast frames can loop again indefinitely. Continuous frame duplication leads to high CPU utilization on switches and network devices, which can cause network slowdowns, packet loss, and even complete network failures. How spanning tree prevents broadcast storms. So it can change the roles of switches as well as ports or interfaces to eliminate loops while maintaining redundancy. It elects a root bridger, right? The root bridge, which acts as a network reference point. Redundant links are placed into a blocking state, and they will discard BPDUs, right, to prevent loops. It uses BPDUs or bridge protocol data units to exchange information about the topology, excuse me. Again, see how we said, well, this one's blocking. On our example earlier, this one was blocking. But this is the redundant path right here. So even though, because they can get to this one through here, as well as through here. And whenever there's a redundant path, it's going to block either this one or this one. And it does this process of, I'm pretty sure it's cost, like the cost, because certain links, like fast Ethernet, gigabit Ethernet, right? They have different costs. And then after cost, or bridge ID, excuse me. The bridge ID is the MAC address and the priority, right? And then if they tie, actually let me pull it up. Root bridge election process. So it's the lowest bridge ID, and then see, because it should be lowest bridge ID, lowest neighboring port ID, and lowest neighboring. So lowest bridge ID. The bridge ID is the MAC address and the priority on the actual device. Give me 1 second. Let me find the actual good slide, alright? Alright, I see where I messed up. Spanning tree, it does the election of the root bridge solely on bridge ID, right? Right here. While the election, like the blocking, to choose which interfaces are blocked, that's the process where it does the highest bridge ID, and then the highest, if that's tied, then you go to the highest neighboring bridge ID, and then the neighboring port ID, right? But that's that's typically for the CCNA if you really want to get into that, right? For now, let's just get back to the just basic concepts of spanning tree, right? So it's gonna elect the root bridge based on bridge ID, which is just a combination of port ID and priority, or MAC address and priority. So the components of spanning tree is the root bridge, the central reference switch selected based on the lowest bridge ID. The root port, the port closest to the root bridge in terms of path and cost. and the designated port, the best port forwarding traffic on a network segment. The blocked port prevents loops by not forwarding traffic while remaining active for failover. And then this is the spanning tree example. This is root ports, RP is root ports, DP is designated ports, and this would be a blocked port. Because it's a redundant path. It has two ways to get to it, and it's going to use this one because it deemed it the lowest cost, and this one as the redundant. It's going to be in blocking to prevent loops. And then these are the states. Blocking, the port listens for BPDUs but does not forward traffic. So blocking, it will receive but it won't send BPDUs, right? And it will not forward regular traffic. Listening, it's a transitioning state. It doesn't forward regular traffic, but it will listen for receive BPDUs. Learning, same thing. It will receive BPDUs, and the port builds the MAC address table but does not forward frames like regular traffic. And then forwarding, the port actively forwards traffic, regular traffic. And then spanning tree convergence. So blocking, the port listens for BPDUs but does not forward traffic. Then it goes to listening. So this would be like if, let's say, you connect a new device, the topology will change. So we'll go through this process, or if a link or an interface goes down and it needs to, so now there's no more loops, it would go into this convergence state, right? So first it will go into blocking. The port listens for BPDUs, but it's not sent forwarding traffic. The port listening, the port prepares to transition, but does not forward frames. They're all able to receive BPDUs though, just not regular traffic until it reaches forwarding. Learning, the port builds the MAC address table, but does not forward frames. Remember, just regular traffic. It does receive and send BPDUs. Forwarding, the port actively forwards regular traffic. Right, and that's it for spanning tree. Let's go now into DHCP, or Dynamic Host Configuration Protocol. So what is DHCP? DHCP is a protocol that allows devices to dynamically get certain settings like IP addresses, DNS, default gateways, things like that, without human configuration or manual configuration, right? Automatically assigns IP and network settings to devices. How it works. So there's a 4-step process called DORA: discover, offer, request, and act or acknowledge. And these are the steps. So discover is the client saying, hey, are there any DHCP servers out there? I need some information. Offer, this is the server talking to replying to that discover request. Yes, I'm here. What do you need? The request is the client saying, oh, I need an IP address. I need my default gateway, DNS server, right? And then it's going to acknowledge DORA, right? Why is it important? Automates configuration, prevents IP conflicts, and simplifies network management. Key benefits: makes connecting devices easy, especially in large or dynamic networks. All right, and then the DHCP process. DHCP discover, the first part of DORA. The client broadcasts a request to find available DHCP servers. Offer, the DHCP server responds with an available IP address and configuration details. The DHCP request, this is the client. The client selects and requests the offered IP address from the server. And DHCP acknowledge, the server confirms the assignment and finalizes the configuration, right? And this is just DORA. DHCP handshake, so discover, the client sends discover to the server sends offer to the client sends request to the server sends acknowledgement to the client. And DHCP components, the client, the device, like end devices, computers, smartphones, printers, smart TVs, anything that uses an IP address basically, that requests an IP address from the network. The server that manages the pool of the IP address and assigns them to devices as needed. The relay agent, a network device that forwards DHCP messages between the client and the servers on different subnets. The IP address pool, a range of IP addresses maintained by the server, ensuring that devices receive unique IP addresses. Right, and then advantage of DHCP. IP address assignment, it allows dynamically dynamically allocates unique IP addresses to each device connecting to the network, instead of having you manually configure each device with an IP address. And then you might forget that, oh, this one's assigned 192.168.10.2, but you're going to assign it to another PC, and then that can cause IP address conflict. It just reduces error from human error, as well as just manual configuration and time for configuring them, right? Additional settings provides other essential settings like subnet masks, default gateways, DNS servers, lease time, allocates IP addresses temporarily, it's the lease period, and recycles them when not in use. Automation. It automates the process of network configuration, significantly reducing administrative overhead. Challenges of limitations of DHCP. Automation. Automatically assigns IP addresses and settings, eliminating manual configuration and reducing errors. That's what we said earlier. Scalability. Supports small networks to large enterprises with thousands of devices seamlessly. Conflict prevention. So ensures no two devices receive the same IP address, avoiding network issues. Flexibility. Ideal for dynamic environments with devices frequently connecting and disconnecting, like mobile or Internet of Things networks. Like, think of this like an airport, right? So how you have many users coming in, going out. So this is very like in high traffic settings like airports. Very useful. Use cases of DHCP. Enterprise networks simplifies managing thousands of devices in large organizations or campuses. Public Wi-Fi automatically configures devices for internet access without user intervention. Data center ensures efficient management of IP addresses for virtual machines and servers. And like we said, Internet of Things like smartphones, Alexa, things like that, right? And did you configure your IP address on your PC or phone? No, that's what your home router does. It acts as like a switch, router, DHCP server, right? And then even sometimes they also do DNS as well. So it does everything locally within that home router. So it goes through that DORA process where a device comes in, it sends a discover message to the router, and then the router proceeds from there, right? Through offer, request, and ACK. And then, all right, this is for configuring a DHCP server or a router as a DHCP server. Let's see, because I'm thinking if we do like an actual DHCP server, or if we do a router configured as a DHCP server, because we could also do LLDP using the router as the switch to actually show you how that looks like. And use port channels to show you as well how LLDP is very useful as well. Yeah, we might do it like that. We'll see. Right. But these are the devices, these are the commands to actually do it, and we'll actually show you it as well in a packet tracer in a lab that we're going to create in a bit. Static mode on end devices. Manually assign. The network administrator or users manually set a fixed IP address, ensuring it always gets the same address. The device does not request an IP address from a DHCP server and does not rely on automatic address assignment. Ideal for consistency, useful for devices like servers, printers, or network equipment that need a permanent, unchangeable IP address. Risk of conflicts. If two devices are manually assigned the same IP address, it can lead to network issues such as connectivity problems. And then this is static mode on PC. I'll show you that in the lab in packet tracer as well. Again, this is like the DHCP or automatic IP address assignment. It requests an IP address from the DHCP server. And then this one is you manually configuring it using static. This is DHCP mode on a PC or an end device. Same thing, PC on the. All right, and we can either do one of these two. I'm thinking. So we can do both. Yeah, we'll do both in one. All right, I see how we're gonna do it. I'll show you in a bit, actually. So we're gonna do this topology, and then have another link, or yeah, cable connecting to a DHCP server right here. We're gonna port channel this using LACP, and then advertise this to the using to this router. DHCP. We'll configure this as in a different subnet, and then configure DHCP relay on this one to show you not only port channel but LLDP as well as DHCP. And I think that's it. And we'll actually show you how to configure the DHCP services on the router. So let's actually get into it. But DHCP is really useful, and so is spanning tree and LLDP. And we did a lesson earlier on LLDP, how it provides a lot of redundancy as well as increases the bandwidth. And we'll show you that again now. We'll just wait for packet tracer to actually load. And then let's start. So we'll do a router here. We'll do a switch here. We'll do 3 end devices. And you can actually, we'll put them in different VLANs as well, just to show you the power of DHCP as well. We'll do this server here. And then we'll connect them as well. Let's do this. I may have to, I should support 2 connections. No. Let me do that. And then let me turn this off, zoom in, and then let me make sure it's off, because sometimes it just magically turns itself back on. All right, not the cover. See, look, it's still on for some reason, even though we turned it off. So it's gigabit Ethernet, it looks like. No, we're just, these are NICs, by the way, network interface cards. They allow for expansion. We'll just do 2 of those. Turn this back on. And then we'll create the port channel here. We'll do like 3 or maybe 4 or 5. We'll see. And just 1 more for redundancy. And look, you can't really see any of this at all. So this is why I want to show you LLDP. And then we'll do it like this, and then we'll also we'll use VLANs from our earlier lecture. I'll actually show you how VLANs work as well here, providing network segmentation and isolation. And matter of fact, let's change this again. I'm sorry. Let's change this to a layer 3 switch. Just because it is way more efficient than setting up router on a stick and just using the SDIs on the switch to actually configure to perform inter-VLAN routing, excuse me. Three, 4, and so we're going to be combining a lot of things here. Some of this you should, well, wrong one. Some of this you should already know if you watched the previous ones. So we'll just do a little refreshing there as well. So now we're going to be combining a few things. And then if you really want to get technical, we'll actually advertise this using OSPF as well. I mean, it should have it there. Yeah. We'll see, actually. We'll just see in a bit. Fine, this is this. Perfect. And then we'll do texts. Just do blend 10. Blend 10.0. They're going to use /24, these ones at the bottom. I'll just fix that up in a bit. And then here it's going to be the SVIs. So we'll do this, blend 10. And then we'll show you SVI. This, and then the port channel. We'll do no switch port. We'll do a /30 here. We'll do 10.10.10.0/30. Here we'll do 11. Put that here, and then let's do this. All right, so let's go into this layer 3 switch, and we'll actually show you the IP helper address command as well. We'll do no and conf t, and then we'll do LLDP run. So this is how to enable it globally, LLDP run, and then you can go into interface configuration mode. Let's just do fast Ethernet 06 and do LLDP, and then you can do either only receive or enable receiving and transmit. But LLDP just makes it run globally, right? But this just gives you more of a granular control, unlike CDP. So here we've enabled LLDP, and then let's create the VLAN. And let's name it HR as well. Let's just give them names. This should be copy. Go here, paste that. Let's name it HR. Name this IT. Name this one sales. Here, name HR. Exit VLAN 20. Name IT. Exit VLAN 30. Name sales. Exit. And then we'll assign the interfaces to those VLANs, all right? So we'll do interface fast Ethernet 06, switch port mode access, switch port access VLAN 10, exit, interface fast Ethernet 07, switch port mode access, switch port access VLAN 20, exit, interface fast Ethernet 08, interface fast Ethernet 08, switch port mode access, switch port access LAN, we'll do 30. Do exit, and then let's add the default gateways. So we'll add it here. Everything here will be set DHCP, and we'll configure the DHCP settings on the server in a bit. So we're not going to touch these at all. We'll just turn on DHCP, but that's after we've configured everything else on this layer 3 switch, the router, and the DHCP server, all right? Yeah, we'll use OSPF actually, because we'll have to add the IP address here. And yeah, and also configure IP routing for inter-LAN routing here. And yes. All right, so IP routing, interface, LAN send, IP add 192.168.10.1, and then it's a /25 /24. No show exit interface. Same thing for LAN 20. Actually, let's go back into interface LAN 10, and then this one's going to be configured. Let me put that here as the second available IP address, and this one. Oops, the first one. So we can already start configuring the helper address. So the command for that is IP helper address followed by just the address of the DHCP server, which is going to be this one. So 11.11.11.2. And this is useful, and especially in this example where the DHCP server is in a different subnet than these, right? So it's going to be like, oh, if this is the IP address of the DHCP server, I'm going to send it there. And it's going to learn that route via OSPF that we're going to run on the router as well as the switch. Right? Pretty cool though, right? So we've done helper address. We'll do interface LAN 20, IP add 20.1. We'll just do up arrow, just to get that same command there. Exit 30, IP add. Up arrow again. All right, perfect. So we've added the helper addresses there, as well as configured the SVIs with an IP address. We've also enabled IP routing here for inter-LAN routing here, as well as let's do this port channel. But before we do that, let's see. I want to show you LLDP. I'll try to figure out which ones are here. Oh. So I'm pretty sure it's all of these. So we'll do no conf C interface range G0, excuse me, G0 1/0 0 through 3. No shut exit. Actually, there's still one that we like. Let's remove these options, preferences. Move this. Still one that's down. Which one is this? And why are they okay? There's one. Let's actually remove that link because alright. So remove that link. It was acting funny. Alright, so as you can see, STP is already working here. Instead of having, I think, 4 interfaces, or yeah, 4 links here, actively forwarding traffic, it's only using one. And then if this one goes down right here, the next one will be up, right? But it's preventing loops since there's multiple connections, right? Now to provide actual redundancy here, we can do interface range again. Actually, we'll do it on the router first, but we'll do LLDP run. Now that we have LLDP run on both of them, it's going to make this configuration a lot easier. So do show, or let me show you the actual command for it. Show LLDP neighbors. And this is going to show you the devices that have LLDP configured on it. Their host name, which is a router. The local interface, which is the interface on the device that you're currently on. So F02. The whole time, if this expires, then it will be removed. The compatibility is just like the type, the device that it's connected to, which would be this router here. And then the port ID is the interface that it connects to on the other device, right? So let's do fast Ethernet. So it makes it a lot easier. So conf t, we'll do interface range, fast Ethernet 2 through 5. And then we'll do no switch port here because we'll actually have to add the IP address. The first available one here and the second one here. All right, and then we'll do channel. To create a port channel, you do channel group followed by the number. It could be random really. 1 and then mode, right? And mode, let me show you. So active is LACP, auto is, LACP is active, and passive is LACP. It's typically the industry standard since it's not Cisco proprietary, like it's vendor neutral, unlike PAGP, which is Cisco proprietary, which will only run on Cisco devices, right? So we'll do active, which means it's actively trying to form a port channel. We'll do that. We'll do exit, and then we can go into interface, port channel, and then 1, which is the group number really. We'll do IP add 10.10.10.1, and then the mask, and exit. Right, and then do show IP interface brief. Port channel should be there. It's currently down because we have to configure this part first, but it does have the IP address, right? Let's go here. Again, remember the command, show LLDP neighbors, and then we'll do conf t interface range G0 1/0 through 3, right? Yeah, through 3. We'll do channel group. Let me see. It may be that it's only good via layer 3 switches. So maybe we'll have to change this topology. So yeah, we may have to change this topology. Yeah, let's go ahead and do that. I really want to show you LACP. So let's see. May have to configure HSRP on it. So we'll do this. We'll do switch port. Exit out of that. Actually, let's go back into that mode and do no channel 1 active. No port channel. Do show IP interface brief. All right, remove the port channel, and let's see how. So if we're going to use LACP, we'll do it in another lab, because this is much simpler, and I don't want to introduce like multiple concepts, because we may have to do HSRP, like have an access layer switch here, and then, or excuse me, a layer 2 switch here that aggregates the connections from the clients, and then up here we'd have like 2 layer 3 switches that have LACP enabled, and then have the interfaces on the layer 2 switch trunk, and then have the layer 3 switches perform interline routing, as well as port channel and OSPF. But for now, we'll just, so yeah, we'll do LACP in a different one. I mean, the video should already be up. So if you want to go ahead and learn about LACP, you can go ahead and watch that one. So let's put this back on, preferences. We'll still use OSPF. So I'll show you how to do that in a bit as well. We've made a video on that before as well. And then let me put this back here. Right, so now we've just enabled them on this. Now let's actually go ahead and start configuring this interface here, and then we'll configure the actual pools on the DHCP server, all right? So we'll do interface IP add. So now that one's up. We just need to do some static configurations on the server. And as well as configure OSPF on this here. But we'll do this one first. So default gateway. Paste. Change this to 2. Make sure it's the correct subnet. Oh, forgot a period. Oops. You go to services, you'll go to DHCP, and then here you can create the VLANs. So VLAN 10 HR. Here you can add the IP address. .1. DNS server, not any for now. Do 192. 168, change this to 10, and then we will add here. So we've added 1, now we just need to add IT, change this to 20, same thing here, and boom. As well as when you're doing this, sometimes the maximum number of users gets sent to 0 for some odd reason, and just make sure you have the users set to a range that's not 1, because it won't be able to get an IP address if you set it to 1 or 0, right? Happened to me before on a lab, and just a little heads up in case you want to do your own packet tracer simulation in lab. Add that, and then we'll turn this on, and that's it. Let me change this to save. All right, so now we have HR. Whoops, let me change this to 20. 20. 20. 20. So HR, plan 20, seems good. 30. And then this one has, let me change this to 10 for some reason. And I did it wrong. Okay. So 10 is HR. 10. Save. HR is 20. No, HR is 10. IT. At this point, let me just change this. IT. HR. Should match up. Line 10. IT. HR is 20. All right. So now we will configure OSPF on these devices. So first, let me do it on this one. So we'll do router, OSPF1. And remember, we're able to do this because we enabled its layer 3 capabilities with the no switch port and IP routing, right? IP routing allows it for it to actually build a routing table. Do show IP route, and these are the ones that it has. So we'll do network 192.168.10.0. And remember, it uses wildcard masks. So /24 would be 0.0.0.255. And remember, this is going to be single area, so we'll just do area 0. And there's this way of doing it, and then there's also another way, which is route summarization, which would just be this. A /16, which would advertise all of them with just a single command, right? So we've done that. Now let's one more. We have to enable OSPF on this interface here. Let's go back here. Network. O.O.O.3 area 0. And remember, easy trick for wildcard masks is actually to get the number 255, which is the maximum number of, like the max of a 250 of range in an octet. It's from 0 to 255. So you get 255, and then you get the mask, right, of 24, or let's say 27. 27 would be 224, I'm pretty sure. Yeah, 224. So you subtract 255 minus 224, and that should give you, let me actually see, calculator, 255 minus 224, 31. So you'd use a wildcard mask of 31 here if you want to advertise a /27 subnet mask. All right, that's just a little trick you can use as well. So we've enabled OSPF on these fast Ethernet interfaces, as well as this one here. So now let's configure this. We'll do router OSPF1, network 10.10.10.0. Network Now let's fast forward a little to see perfect deform in adjacency. Exit again, show IP route. Perfect, see it learn 3 networks. Went to this VLAN, this VLAN, and this VLAN. And then see and show IP route. It learned 1 to this DHCP server. So now let's actually do simulation mode. Go into here, into DHCP. We'll have all of them configured with DHCP just to show you that it is able to go to the server. And we'll inspect it here as well. So it's going to go to their default gateway. It hasn't been configured yet, and then we'll show you, because it should populate that it's using the helper address. The packet matches the helper criteria. The device forwards the packet to the helper address. The device looks up the destination in the routing table. The routing table finds the route to the entry of the destination IP and can be reached via 10.10.2. Right. So it's very important that you use the helper address since it's in a different subnet, as well as OSPF for it to actually learn the route to there. Boom. All right, now let's click on them. This one doesn't have it. Neither does this one. So let's actually do some. All right, this one does. This one does now as well. And so does this one. So it's just running through the DORA, the discover, offer, request, and acknowledgement, right? CVV, boom. See, we didn't touch them at all. We just enabled DHCP. Now let's see if interVLAN routing works using the layer 3 switch. Ping 10 192.168.20.2. It should be the second one. Let me just make sure. 2 and 2. So we'll just ping there to see if it goes through. So it goes through here, and then the layer 3 switch will handle the interVLAN routing. That's ARP. Perfect. So we've confirmed interVLAN routing. Now let's just do 3 or 30. Perfect. So confirm them and confirmed interVLAN routing. Configured OSPF for it to advertise the routes, as well as used SVIs as the default gateways. And just to show you, gateway is the SVI there. All right. As well as configured a DHCP server with pools for each of these VLANs and confirm that they're able to get their information via DHCP without manual configuration, right? And that's pretty much it for the lab, guys. Hopefully you liked the video. Thank you and see you in the next one. Bye.